Hello everyone, welcome to our second lecture. So today we'll be looking at part 1 of 2 on energy and biochemistry. So we're going to aim to answer this question. So keep that in mind as we go through. What determines if a reaction is possible? So the concepts we'll look at today are thermodynamics, we'll look at enthalpy, entropy, Gibbs free energy, and ATP hydrolysis coupling. So again, we're going to go over thermodynamics we talked about briefly last lecture. So the first law, so what makes a reaction possible? It is the first law of thermodynamics. So again, this law states that energy is neither created or destroyed, but changes form. Energy change in a system can be defined by something called enthalpy. And enthalpy involves the movement of heat, essentially. So it's the heat content of a molecule. So the first law of thermodynamics involves the transfer of heat between a molecule and its surroundings. So enthalpy means heat content and is represented by the symbol H. So you'll see this quite often. So here we have change in enthalpy. Our heat content is represented by the delta. So delta here is that triangle, is a symbol used to denote change. So we have change of H. Change in enthalpy. So heat can be lost, which is negative, or positive, or gained by a molecule. When heat is lost, the temperature of the surroundings increases. So again, if the heat is lost from this molecule, it's removed, and then the temperature will go up in the outside. When heat is gained, the temperature in the surroundings decreases. And we'll see how temperature and heat content relate to disorder and how we mentioned disorder in the last lectures. So change of H, so enthalpy. So change in enthalpy is represented by the equation. So we have H final, which denotes the final temperature of the molecule, and H initial. So that would be, usually it's written as HF, HI. It denotes the initial temperature of the molecule, so you'll see these in the formulas. So when change of enthalpy is positive, the final temperature of the molecule is greater than the initial temperature of the molecule. It has therefore gained heat. So positive, gained heat. When the change of H is negative, the final temperature of the molecule is lesser than the initial temperature of the molecule, and the molecule has been lost. The heat has been lost, sorry. So again, negative change of H is called an exothermic reaction. So an exo. So a molecule, in this case, the molecule loses heat. So we have initially high temperature. The initial temperature is higher than the final temperature. So here we can see our initial temperature, negative change of H, therefore it's losing our exothermic. So we have our exothermic. And then our final temperature is lower. So again, exothermic energy is released from the system. So again, in this case, the surroundings gain heat, and when the molecule loses heat, it simply goes into the surroundings. So remember, our first law of thermodynamics is not lost, it just changes form. So an example, our initial enthalpy is 20 joules, while our final is 5 joules. So here, simply put, our H initial, H final minus H initial equals negative 15. So therefore, it is exothermic, and energy is released by the system. So now endothermic. So again, a positive change of H is endothermic. So in this case, the molecule gains heat, and the initial temperature is lower than the final. So here, we're going up, initial, from the initial to the final. So the surrounding loses heat. So when a molecule gains heat, the heat is taken from the surroundings. So here's our example again. We have our HF, our HI. And this is positive 15. So again, this is endothermic reaction, where energy is required by the system. Key is required. So what else determines a reaction? So now we go to our second law of thermodynamics. So again, that stated that all processes increase entropy, which is known as the decreasive degree of disorder in the system. Energy change in a system can also be defined by entropy. So entropy is the order or disorder of the molecules in a system. So when we have higher entropy, i.e. higher disorder, the lower the energy in the system. So higher disorder. Lower entropy, where there is disorder, less disorder, higher energy in the system. So entropy means disorder and is represented by the symbol S. So again, we see this change, delta symbol, change of S. So change in entropy is represented by this symbol, and the units are in joules or degrees Kelvin. So degrees Kelvin, if you haven't heard of it, is essentially you can be converted by degrees in Celsius plus 273. So for example, we have it's 20 degrees outside. To get degrees Kelvin, we would need to add 273. So this is just a quick conversion. So entropy can be lost or gained by a molecule. So this is important here, guys. So entropy is affected by three factors. It is affected by the arrangement of the molecules, the number of molecules, and the motion. And we'll talk about these in detail in a second. So first, the arrangement of molecules. So here we can follow the figures as I speak, but here in a tight arrangement, there's less entropy, so less disorder. So here you can see, if you kind of just think about what the word disorder means, this is very compact, less disordered. Where we have a loose arrangement, there's more entropy. So we can see here, we can see here we're moving from a state of low to high, high to low here. Again, this arrangement of molecules related to the state. So we have our solids, liquids, and gas, which you've definitely heard about. So you can kind of predict here how we move along the scale of entropy, with our solids having the tightest arrangement, slightly looser in the middle, and then our gas being very loose. Now the number of molecules. So simply, more molecules equals more entropy, less molecules equals less entropy. So again, this would be less disorder, and then more and more. So here you can see entropy increases with the number of molecules. So motion of the molecules. So again, more motion equals more entropy in the system, while less motion is less entropy. So you can think liquid versus gas. The molecules in a liquid will still move, but they're not as much as a gas. Where in a gas, they're flying around very fast. And this is also related to pressure. So here, more pressure equals less motion, which therefore means less entropy, and therefore more energy. So if we think about just a pressure system, if we have a lot of pressure, the molecules are very condensed and have less entropy, but there's a lot of potential energy. So if you unleash that pressure, there's going to be a lot of momentum, or not momentum, but a lot of energy being released. And compared to a large place or a large container where there's less pressure, but this allows the molecules to move more space and stuff like that, and therefore there's more entropy or disorder, but less energy. So again, our change of S. So change of S is represented in equations where we see S final and S initial, which again is the final entropy and initial entropy. So when change of S is positive, the final entropy of the molecule is greater than the initial entropy of the molecule, and it has become more disordered. When change of S is negative, the final entropy of the molecule is lesser than the initial entropy of the molecule, and has become less disordered. So again, just to check up, I want you guys to answer this on your own, but we'll go through it. So we talked about entropy and enthalpy. So again, we talked about our heat. We also talked about our entropy with our disorder and stuff like that. But again, these are all applicable, but just keep that in mind. So what is the enthalpy and entropy of water boiling? So the reactant would be the liquid water, and the product would be water vapor. The heat of the reactant versus the product. So for example, there's less heat in the liquid versus more heat in the gas. So if you think about boiling water, you got to add that heat to get it to that gas state. Then we have the state versus the reactant product. So reactant is a liquid and the product is gas. So our change of H would be endothermic through a positive H through the gain of heat. So we're starting from that H initial, going up to our H final of a higher temperature and more energy. And we're also gaining entropy with a positive S. So now moving on to Gibbs free energy. So Gibbs free energy combines the concepts of enthalpy, which is H, and entropy, which is S, in the term of G, expressed as kilojoules per mole, and is usually expressed as change of G, but we'll get to that later. Gibbs free energy represents the maximum amount of energy available to do work, and the focus on energy of biochemical reactions. And we'll talk about Gibbs free energy in a lot of our chemical reactions and glycolysis and stuff like that. So change in Gibbs free energy is also represented by certain equations. Gibbs free energy can be lost, which means it's a negative G, or gained, which is a positive change of G, by a molecular system. So instead of exothermic and endothermic, we have exergonic and endergonic reactions. So change in Gibbs free energy that is negative is exergonic reaction. This means the reaction or system releases or loses energy. And again, this reaction occurs spontaneously. So this is very important. These spontaneous reactions are very important in our pathways within our body, because these spontaneous reactions happen essentially without effort, but it's not that simple, but we'll get to it in more detail. Where a positive change in Gibbs free energy is endorganic, and the reaction system consumes energy. So consumes, we need usually through ATP. So we'll talk about in glycolysis as we go through the pathways. This reaction is considered endergonic because we need to put energy in. And again, this reaction occurs non-spontaneously. Sorry about that, guys. Had to pause. So, conditions that favor exergonic or spontaneous reactions. So, this occurs usually when it's energetically favorable. So, these reactions will be spontaneous and exergonic, and will involve the loss of heat and or the gain of entropy across the reaction. So, this means that reactions with a negative change of H, so enthalpy, is exothermic, and with a positive change of S are energetically favorable. So this is the preferred state usually. So note that temperature can also be a factor. Remember the equation. So again, if you think about different body systems, and like one of the key examples in fever, so sometimes in fever enzymes can be more active in certain temperatures and help with our immune response. But anyways, we'll get in more detail about this later. So this is a really good summary in understanding change of Gibbs free energy, which is the change of H minus the temperature and change of S. So again, we got our enthalpy and our entropy and our temperature, which is in degrees Kelvin, if you remember. So if we have a negative enthalpy, positive entropy, and a negative change of Gibbs free energy, is therefore exergonic. Positive enthalpy, negative entropy, Gibbs free energy is positive, endergonic. So here's where it gets a little different. So here we both have a negative and negative enthalpy entropy, but a positive or negative Gibbs free energy. This can be exergonic if, it's exergonic if change of H is less than temperature times change of entropy. Whereas it's endergonic, again, this can be positive, can also be positive or negative Gibbs free energy if this is greater than that. So keep that in mind. So Gibbs free energy versus Gibbs standard free energy. So again, Gibbs free energy represents the maximum amount of energy available to do work. It is of multiple importance to all life form. So again, Gibbs free energy represents what is actually happening in a living cell and the conditions that are constantly changing, compared to Gibbs standard free energy, which is measured under constant laboratory conditions, which do not change. So this is Gibbs standard free energy is commonly given in biochemistry, since change in free energy is hard to measure accurately in dynamic in vivo conditions. So it's hard for us to definitively say what the Gibbs free energy, the true Gibbs free energy of a reaction is, compared to Gibbs standard free energy, which is what our laboratory measures, which might not be 100% representative of what's actually happening in the body, but they're quite similar. So how are these values obtained? So Gibbs standard free energy is usually measured under standard laboratory conditions, where we have reactants and products. So when a reactant equals a product, it equals 1 mole. So again, M is moles per liter. So for example, at 25 degrees, so remember plus 273 equals 298 degrees Kelvin, and at a pH at 0. We need to have these all standardized, or know them at least. So because change in free energy, Gibbs free energy values determine whether or not a reaction is energetically favorable, and therefore the reactions are spontaneous or non-spontaneous. So for a reaction where the Gibbs change in Gibbs free energy is negative, energy is released by the reaction, and the reaction is termed exergonic, as we said, and the reaction will occur spontaneously. But we must rely often on Gibbs standard free energy values, since this value are always changing and very difficult to measure 100% accurately. So again, the rule here is Gibbs free energy and Gibbs standard free energy for a given reaction usually correlate. So it's not like they're not accurate, it's just they're not the exact number. So you can't definitively say what the Gibbs free energy is. So examples of Gibbs standard free energy in biochemistry. So here unidirectional arrows mean, we'll see these a lot as we go through our pathways, where this indicates irreversible reactions where only operate in one direction. So in this reaction, we can't go back. Glucose 6-phosphate cannot go back to glucose. This reaction is irreversible. But in comparison, where we have bidirectional arrows, where we can see here, fructose 6-phosphate can go back to glucose 6-phosphate, and this indicates a reversible reaction. It operates in both directions. Here we can see the values to see how high the exergonic this reaction is, and so therefore is very spontaneous. These numbers indicate, essentially, they kind of give you an insight into how reversible a reaction is. So if you didn't have anything else and just knew this reaction was a high negative score, it's likely not reversible. In comparison to this, where we can see we almost had a positive, so it actually is reversible. So consider this reaction again with a large positive Gibbs standard free energy. So here we have a formula. So we have glucose, and forming our glucose 6-phosphate plus water. In this reaction, we have a positive 13.8 kilojoules per mole Gibbs standard free energy. So this Gibbs standard free energy is largely positive, and therefore the reaction irreversible, non-spontaneous, and energetically favorable. So as I mentioned, even though there's a large negative, the large is essentially based on the quantity, I say the largeness of the number. So again, if this was a large positive, it still can be irreversible. It's not just negative versus positive. So the problem here is that the reaction does not occur on its own, but we need it to. So even though this is positive, so likely energy went in. So here we have our phosphates. And likely, so we can see here that clearly reaction occurred where water is removed. It's still irreversible. So a solution in this scenario is using ATP hydrolysis. So again, that's where that water came from, to make the reaction energetically favorable. So the hydrolysis of ATP is an exergonic reaction that releases lots of energy, which we've talked about several times in biology and earlier in our first lecture. So we can use ATP to change Gibbs standard free energy of a reaction on the previous slide from a positive to negative through the coupling of ATP hydrolysis. So this is usually called ATP coupling. So this reaction becomes energetically favorable. So here we can see our adenosine AMP, ADP, and ATP. So this is the molecule we all know is that energy molecule. So we can see in comparison to ADP, ATP has a high energy phosphoryl groups, 3, in comparison to the 2 in ADP. But even though these are both higher energy, this is higher energy. So we can still go from ADP to AMP and still release energy. So some reactions will go from ATP, ADP to all the way back to AMP and then build it up again. But it's more common to go from ATP to ADP. So again, coupling of ATP hydrolysis. So again, we had that reaction from 2 slides ago where we had that large positive Gibbs free energy. Standard Gibbs free energy, sorry. So now we have action, but we now have ATP hydrolysis. So we have our ATP and H2O, where we get our ATP and then our phosphates. Now we have this large negative. So again, if you can solve here, you can essentially add the two values here, and then based on that number, you can decide whether it's negative, positive, exothermic, endothermic, and so on. So in summary, ATP coupling. So again, just to say, this would be our 13.8 plus our negative 30. Let me just punch that in. Sorry about that. Doing this on my phone, probably not the best choice. So here we get negative 17. Sorry for being so slow. Again, kilojoules per moles. Hopefully you guys are on a speed up version so that doesn't feel as slow. But yeah, so again, summary, ATP coupling involves the removal of high energy phosphate from ATP, becoming ADP. This provides a means to change from endergonic to exergonic. So remember, exergonics are more favorable and usually spontaneous. So again, I'll let you guys look at this one. So I'll leave it here for a second. So again, when we have Gibbs standard free energy like this is essentially, we can see here, this is our standard equation. So now we just have to rearrange the equation to solve Gibbs R1. So I'll let you guys solve that one out if you want, just for some practice. But yeah, moving on. So summary. Two things determine if a reaction is favorable. One is the enthalpy, which is the heat change. So remember, we have endothermic and exothermic. And our entropy, where we have endergonic and exergonic, and that's disorder. Again, exergonic reactions are spontaneous and more favorable, so usually with a negative enthalpy and a positive entropy. Gibbs free energy combines enthalpy and entropy as well as temperature in degrees Kelvin and correlates with Gibbs standard free energy. And coupling reactions make non-favorable reactions favorable. So just again, another recap. Enthalpy is change of H, which is the heat energy constant of a system, whereas entropy is the disorder of the system and is inversely related to energy. And entropy depends on molecular arrangement, as we said, number, and motion. And we also say pressure can get involved as well. And again, Gibbs free energy is the overall energy of a system, and it's the max amount of work. The Gibbs free energy determines whether a reaction occurs or not. So that's the end of our first energy lecture. So I'll see you guys in the next part. See ya.